Welcome to the last lecture of the lecture course. Last time we discussed the Chern-Simons invariant of oriented compact three-manifold, and today we want to do something with it, we want to apply it. And so throughout, for the rest of the section, throughout I will denote by M a compact, or by N, compact oriented three-manifold, so that I don't have to repeat this all the time. And the first observation we want to make is the following lemma, namely, if we have a covering, so if n tilde, some metric g tilde to n metric g is a k-fold covering map, and it's a Riemannian covering, so it's a local isometry. Let's say that too, Riemannian covering map. Then the corresponding Chern-Simons invariance just multiply that. So Chern-Simons invariant of the covering space is k times Chern-Simons invariant of the original manifold. Of course, always take the modulo z, right? So this is invariance in R modulo z. And why is that? Well, it's actually quite simple. Namely, in order to compute the Chern-Simons invariant, we have to choose a flat background connection and the global sections, global framing. So let's do that for M. So let E1, E2, and E3 be global orthonormal frame on M, and then the corresponding flat connection is the one for which these fields are parallel. So let's nabla 1 be the corresponding connection for which we declare E1, E2, and E3 to be parallel. And this is then automatically a flat connection. And now the Chern-Simons invariant of M can be computed with respect to this flat background metric using the Levi-Civita connection of G. And in order to compare with the space M tilde, what we simply can do is we can take these fields and pull them back to M tilde, and then the corresponding connection also pulls back. So pulling back. And since it's a Riemannian covering, it's a local isometry. When I pull these back, this gives me also again a normal frame. Pulling back to M tilde yields E1 tilde, E2 tilde, E3 tilde, global ON frame on M tilde with corresponding connection nabla 1 tilde. Corresponding flat connection nabla 1 tilde. And now the integrand that we need to integrate over the manifold in order to get this invariant, so the Chern-Simons integrand. Remember this, if I do this with respect to such a global frame and its corresponding connection, which just looked as follows. If you take the trace of omega, where d omega minus 2/3 omega cubed, right, up to some constant involving pi. And this three form has to be integrated over M to give me the Chern-Simons invariant. And now if I consider, so over here, omega is the connection matrix, connection 1 form of the Levi-Civita connection. for G with respect to this frame E1, E2, E3. Now, if I compare this with the corresponding form on M tilde, when I take the connection form for the Levi-Civita connection of G tilde with respect to this back frame, then get this corresponding expression here. But the pullback of omega exactly gives me omega tilde. So this whole expression pulls back to this expression. So that means if I pull this back, let's call this phi. If I pull this back, and I get this. And then it's clear that if you integrate over M tilde, this expression here, okay, so omega tilde, wedge E omega tilde, and so on, and you compare this to the integrand of that form of M, so that's a multiple of the volume form, that's a multiple of the volume form you pull back, and then then you have a k-fold covering, and then you just get k times this integral. And so this is then identical to the Chern-Simons invariant of M tilde modulo z, and this one is k times Chern-Simons of M modulo z. Oh, I forgot this constant, but it doesn't matter, right? All right, and let's write as an example. Look at the manifold M equals S3 with the usual round metric, curvature 1. Then, so that's actually in this setup, that would be my manifold M tilde. And for manifold M, I take RP3, which remember is the same as SO3, also with the round metric. So that's a twofold covering of that, Riemannian covering. And then the lemma tells me that the Chern-Simons invariant of S3 sphere with the round metric is 2 times the Chern-Simons invariant of a real projective space, SO3, with the round metric. And this can be computed to 1/2, so that is 1, which is the same as 0. So in other words, the Chern-Simons invariant of the sphere with the standard metric is trivial. All right, good. So let's keep that in mind. We will need this in a moment. So, one important observation is now the following proposition. If I have one metric and one manifold and 2 different metrics on it, and if they are conformally related, then the Chern-Simons invariant is the same. So let's specify this. So let G and G tilde be conformally related metrics on M. And then Chern-Simons invariant of M with the metric G, the volume size is that of the metric G tilde. So it's a conformal invariant. It's not always the same. We have seen this or mentioned it last time. If you provide SO3 with the 1 parameter of natural metrics here, we have seen that the Chern-Simons varies with that metric. But if the metrics are conformally related, then the Chern-Simons invariant is the same. So why is that? Proof, or idea of proof. So GE. So again, we need background sections and metric and connections in order to write down the integrand for this one. So that E2, E1, E2, E3, again, the global orthonormal frame on M with respect to the metric G. Okay. And now that the metrics are conformally related, means this metric is a function times that metric. So let me write it like so. Write G tilde equal to, and the function must be a positive function. I write as e to the 2f times g, where f is some smooth function on f. So that's what it means to be conformally related. And then we can get from this one a global orthonormal frame for the other metrics simply by, so they are still orthogonal but no longer norm. So I just have to rescale the vectors. And so then Ej tilde equals e to the minus f times Ej. This then yields global orthonormal frame with respect to G tilde. And this we use to compute this side of the equation. And okay, now we need to control this integrand here, where the curvature for, or the connection form of the Levi-Civita connection enters. We have to compare these two. So we have to compare the two different Levi-Civita connections. And this can be written down. So you write Levi-Civita connection for G tilde I denote by nabla tilde, and the one for G I just denote by nabla. And then there's a correction term involving the derivatives of f, which I don't even want to write down. You look this up in the literature. What's more important to us is how the curvature, how the connection forms, how these connection matrices relate. And then, well, you compute that the connection matrix for nabla tilde with respect to the tilted frame is given by the connection matrix for nabla with respect to the untilted frame plus a correction term which I can give you. So this is differential of f applied to j times vi sharp minus df I times j sharp, where the sharp here means it's the musical isomorphism for the metric G. So right, the EIs are vector fields and the EI sharps are one-fourths. So that's a function times a one-fourth. Function times one-fourth. And you also see that these things are anti-symmetric in I and J because they come from metric connections, and this expression is also anti-symmetric in I and J. Looks good. Maybe yeah, that's true. The coefficient functions have the indices downstairs. What you then do is you take this formula and you insert it in the in this integrand and compare with that integrand and see what the difference is. So then you need to compute so take the corresponding expression for tilted forms mine. And compare this with the untilted ones. Then you get something which I don't want to write down. The important thing is it's exact. So that's the whole point. And then if you integrate, this term drops out. Integration and Stokes yield. I'll conclude the proof. So I don't want to would cost us precious time, which we don't have much left. Okay, and so why is that interesting? Well, you could now use this to prove that certain metrics are not conformally related, but then you might say, well, I see this directly if two things are conformally related or not, right? But you could also have a metric which, when pulled back by diffeomorphism, is conformally related to G tilde. And if you pull back the metric by diffeomorphism, then the Chern-Simons invariant doesn't match either, because this diffeomorphism will be an isometry between the two manifolds. And the Chern-Simons integrand will be the same, and the corresponding one, and the integral will be the same. So you might have two different metrics, such that when pulled back by some strange diffeomorphism becomes a function times the other metric, and that's not so easy to see, or to rule that out. So for this kind of thing, this might be useful. But I will also give another application, which is this theorem. If mg has a conformal embedding, oh no, not necessarily embedding, actually immersion into R4 with the Euclidean metric, then the Chern-Simons invariant must be trivial. And so you can use this to rule out conformal immersion. So let's see why that is true. I will do that. All right, so let's assume we have a conformal immersion. So let iota from M into R4 be a conformal immersion. So that means if I pull back the Euclidean metric here to M, then that will be conformal to G. Right? So iota star of the Euclidean metric is conformal to the given metric G. And now, by the conformal invariance of the Chern-Simons invariant, we can replace this metric G by this pullback metric. This will not change the Chern-Simons invariant. And therefore, we can, without loss of generality, assume that iota is actually an isometric immersion. Okay, so the position implies that without loss of generality, can assume that iota is not just a conformal immersion, but actually an isometric immersion. So let's assume that. And get a vanishing of the Chern-Simons invariant. Okay, and in order to proceed, we look at the Gauss of this immersion. So that's a map from the manifold M to the unit sphere in R4, which sends a point x in M to mu of x. And what is mu of x? So where mu of x. All right, so what I do is, so I take the point x in my manifold M, I consider the tangent space at that point to M, and then I have this immersion into R4. So let me use this immersion to push this tangent space forward. So I take the differential of iota x applied to that. This gives me a three-dimensional subspace of the corresponding tangent space of R4, but the tangent bundle of R4 is canonically trivialized, so I want to identify this with the three-dimensional subspace of R4 itself. So I want to consider this as a three-dimensional subspace in R4. And this should be the normal. So I'm requiring that this is orthonormal to that, so that gives me a vector in Rn. It should have unit length so that we are in S3. And this specifies this vector up to sign, right? So this specifies the direction, that specifies the length. And the orientation has to be fixed still. But remember, we are only dealing with oriented manifolds M here. And so if we take a positively oriented basis of this tangent space, so E1, E2, E3 are positively oriented ON basis, let's say, of Txn, then we can look at the corresponding image vectors. D iota x, d iota of 1, and similarly for 2 and E3. So that gives me some basis of the image space, and I complement this with nu of x, then I demand that this is a positively oriented basis of alpha. So that fixes the direction. So remember here, so this is not an embedding, right? So if this was an embedding, then indeed this would be a hypersurface in R4, which would bound some domain, and then you could talk about the exterior and interior. You can't do this anymore here because it's just immersion, so it can have self-intersection, etc. But still, this construction makes sense. So that's the Gauss map. That gives me a nice map to the unit sphere, which is also an oriented compact three-manifold. And so if we now look at this diagram, so we have this map mu from M to the three sphere, and here we have the tangent bundle of the three sphere, and here is the manifold M. And now I claim that there's a natural bundle map from here to there, which is a fiber-wise isometry. Namely, if you have, for any point x in M, you have that this image here, this image space, well, this is orthogonal to u, so that's the orthogonal complement to u of x actually. And for the sphere, we also, the orthogonal complement of the base vector is exactly the tangent space. So that's also naturally identified with the tangent space 2s3 at the point mu of x. So this map d iota maps the tangent space of M to the corresponding tangent space here. So we have this map d iota here. And since the whole thing is an isometric immersion, this means that this is a fiber-wise isometry. Right, so that's fiber-wise isometry. Right. So here we have this bundle map from M to S3. Now, let's look at the Levi-Civita connection of the sphere. The Levi-Civita connection of S3, or let's say on the tangent bundle of S3. So that's a metric connection on this tangent bundle, which in addition is torsion free. If you pull this metric connection back along this bundle map, you get some metric connection here, and then you can check that the torsion freeness persists. So in other words, the pullback of the Levy-Cheever connection here gives you exactly the Levy-Cheever connection there. So this pulls back to the Levy-Cheever connection on the end. All right. So if we now look at the Chern-Simons invariant, so we still have to specify a background frame, but it's obvious what we do. So we first choose a background frame on the three-sphere. So let E1, E2, E3 be global ON frame on S3. Pull it back along iota, then Ej tilde, which is d iota minus 1 of Ej, so it yields a global ON frame on M. So now we have our background frames with respect to which we can compute the Chern-Simons invariant. And then, since everything on M tilde is obtained by pulling back corresponding things on the three-sphere, the same thing holds for the connection form, and hence for the Chern-Simons integrand. So then, omega tilde is nothing but the pullback on omega, and therefore, if I integrate over M this transgression thing, this Chern-Simons integrand, I do the same thing on the sphere. So then, well, this is again something times the volume form. Similarly here, we have pull things back, integrate here. So when we compare these things, then we get that this guy is the same thing as that guy times the degree of the map. So that's the degree of the map of the Gauss. All right. And so modulo z, and again I forgot this coefficient involving the pi. Forgive me for that. So this will give me mg, and this will give me the degree of mu times Chern-Simons invariant three-sphere with the round metric. But we just saw that this guy is 0. So therefore, the Chern-Simons invariant is also 0. So, and here's an example where this applies directly. Namely, so certainly this is consistent with the fact that the three-sphere embeds isometrically into R4. Three-sphere has vanishing Chern-Simons invariant, but do the same thing for RP3. Then remember, RP3 has non-trivial, the round metric has the Chern-Simons invariant 1/2, which is not equal to 0 modulo z, and so therefore there's no conformal inversion of RP3 into R4. And that's remarkable in so far that locally this manifold is isometric to the three-sphere, and the three-sphere embeds isometrically into R4. So we have local isometric embeddings, certainly. So locally, RP3 embeds And also, on a global level, there do exist emergence of RP3 into R4. But they are just like conformal. There exist emergence of RP3 into R4. And the first ones, to my knowledge, have been constructed by John Milner in 1950 something. What is it, 56 something? Yeah. And, so this is as close as you can get to having such an immersion. Locally it works, globally it also works if you drop conformal, but you cannot do both things at the same time. Alright, so this is one of the applications of this Chern-Simons invariant, so that you can use it to rule out the existence of conformal immersions of three manifolds. Good. Now, questions about this whole Chern-Simons business? Not at the moment. Then I want to use the rest of my time to discuss Stiefel-Whitney classes. Stiefel-Whitney classes do not quite fit in the approach that we are using with differential forms. On the other hand, I cannot teach a course on characteristic classes and never mention Stiefel-Whitney classes. So that's why I want to discuss them briefly, at least, and also give you some nice application. And so, therefore, sort of wrap up things. So let's talk about Stiefel-Whitney classes. Good. Now, okay, let me start right away. I claim that for each real vector bundle on a manifold, real vector bundle F on a manifold M, there exist homology classes. Now there exists a unique homology class called the Stiefel-Whitney class, W of F, which is a mixed homology class like Chern class or invariant class, and we will see its theory is very similar, very analogous to Chern classes. So, and we start with a 0 degree something in H0, then we have W1 in H1, W2, and so on in H2. And so in case of Chern classes, there was this dimension multiplication here. First Chern class took place in H2, second Chern class in H4, etc. But for Contiagin classes, we even had a multiplication by 4. First Contiagin class lives in H4. Here, the corresponding class is similar. There is no multiplication here. So W1 lives in H1, W2 lives in H2. So all cohomology degrees occur. So that's the cohomology of the manifold M, however, with Z modulo 2 coefficients. And so this is not good for a description using differential forms. Take your favorite definition of cohomology with coefficients in Z modulo 2. If you don't have any, then I recommend to take the algebraic topology class next term. Then you will learn about these general cohomology theories. And anyway, so it doesn't really matter. So just take them for granted now, right? So these are somehow associated to our spaces to our manifold M. They are also in some sense related to the other cohomology classes, and so this is where the Stiefel-Whitney class lives. And it has the following properties, and let me list them. First, the corresponding parts in the cohomology in the Stiefel-Whitney class vanish for all indices larger than the rank. And you will see this. I will list 4 conditions here, which are completely in complete analogy to the ones for Chern classes. So Wi of F is 0 whenever I is larger than the rank of the bundle F, type dimension F. So that's the first thing. Secondly, if we have a vector bundle map, so we have a map from N to N, map here, bundle here, total space of F, total space G here, and then some map here, and this map should be a fiberized isomorphism. Don't have to give it a name actually. So that's a fiberized isomorphism. If you have that, then the Stiefel-Whitney class of G can be obtained by pulling back along the space map the Stiefel-Whitney class of F. Of that. Thirdly, we have a formula for the sum of 2 bundles over the same base manifold. This is also familiar. Just as for Chern classes. And the last one is that, well, these 3 conditions would still be satisfied if I simply define the Stiefel-Whitney class to be 1, right? And put all these W's equal to 0. That would still satisfy all these conditions. So we have to have one condition which makes the whole theory non-trivial. And so I have to demand that the W, the Chern class W1 should be non-trivial, at least on one bundle. And in fact, that's what I'm doing. I take the tautological line bundle of RP1. And that should be non-zero. So there, this is the tautological real line bundle of P1. Here the corresponding statement for Chern classes involved complex projective space. Now we use real projective space. Alright, so these are the conditions, and so this kind of classes exist satisfying these conditions, and they are also then uniquely determined by these conditions. And the construction, of course, is, so you see this is very in complete analogy to the theory of Chern classes for complex vector bundles. But the construction, of course, is now has to be something very different, because we cannot use differential forms to do it. There are different ways to do it. If you want to see how this, most of the time, it doesn't really matter how the construction is done. The only thing you need to know is that they exist and that they have these properties. If you want to see how it works, I recommend the book by Milner, which is listed in the Moodle. So in that book, the whole theory of characteristic classes starts with Stiefel-Whitney classes, actually, before they even talk about Chern classes and invariant classes. So, as in a way, those are the simplest ones, because Z modulo 2 cohomology, computing things modulo 2 is quite, makes things even simpler. Anyway, so once we have that now, so we now should believe that these classes exist and have these properties, that they have these properties. Now let's draw a few conclusions, consequences. So first of all, I can look at the special case here, where this bundle is obtained just by pulling back that bundle. Okay, take the pullback bundle. Then we do have this fiberwise isomorphism, and then the thing applies. So then I could write this condition 2, in this case, that the Stiefel-Whitney class of the pullback bundle is the same thing as the pullback of the Stiefel-Whitney class. But also, I can apply this when the base map is actually the identity, M and N are equal. And then we have two vector bundles over the same base manifold, where we have fiberwise isometries. In other words, we have a vector bundle isomorphism. And then this actually tells me that the Stiefel-Whitney class does not change under vector bundle isomorphisms. So if I have F isomorphic to G as a vector bundle over M, then the Stiefel-Whitney class of F coincides because it's pulled back along the identity map, so they Stiefel-Whitney class coincide. So that's another. And these two things combined, and then I'll give you back this condition. Another consequence is if your bundle is trivial, then the Stiefel-Whitney class is trivial too. Contains only this H0 part. 1. Why is that? Well, if the bundle is trivial, you can again use this condition 2. If it's trivial, then as your manifold n, you can choose a point, and you map your whole manifold to the point. And then a vector bundle over a point is just some fixed vector space here. If you pull that back, this gives you a trivial bundle. And then the Stiefel-Whitney class must be the pullback, but the point has cohomology only in H0. And therefore the other Stiefel-Whitney class have no chance to live because there's no space for them at the cohomology of the point. Okay. F can be pulled back from a point. So we just write that so. All right, so I guess that's pretty much what we need to know. And so these are immediate consequences of these conditions here. And then with some more effort, but pretty much analogous to what we did for Chern classes, you can find more analogous statements. Namely, the facts. There's a question? Yeah, okay, good. So RP1 is the same as S1, right, as a manifold. And what's the cohomology of S1? In particular, what's the first cohomology of S1? It's Z modulo 2. And indeed, yes. So demanding that it's non-zero specifies this class completely. Yeah, good question. All right, so now, in a similar way as we did for complex projective spaces in Chern classes, we can actually write down the cohomology, and that would also answer the question, namely that the cohomology of Rpn with Z modulo 2 coefficients, in fact, is always Z modulo 2 polynomials generated by one element. So in each degree, it's just generated by the corresponding power of A, modulo A to the n is first power, because the cohomology in larger than the dimension is 0, where A is indeed exactly this uniquely determined first Stiefel-Whitney class, but of the tautological line bundle of Rpn in H1. And that's non-zero. analogy to complex projective space. There we looked only at even degree homology. The odd degree homologies were 0. And the even degree homologies were one-dimensional and generated by powers of the first Chern class of the topological. It's exactly the same thing. Okay. And also, the other thing that I'm now mentioning will also look familiar to you, namely, if we compute the Stiefel-Whitney class of the tangent bundle. So this will be an expression in this generator A. And what do you guess? You can guess it. What is it? Which expression in A? Let me write plus, because minus and plus is the same anyway. And the first. So the same formula that we had for the tangent bundle of complex projective space in terms of the Chern class of topology. And the proof is also the same, really. So you use the same characterization of the tangent bundle in terms of homomorphisms from the orthogonal complement to the topological bundle, etc. And embed it in the trivial bundle and so on. The proof is exactly the same. And you could literally translate it, no problem. Good. So we have that too. But now we come to something which is new, and that is if RPN is parallelizable. Then we have a restriction of dimension, namely m plus 1 must be the power of 2. Only in these dimensions can we have a can be parallelized. And why is that? Okay, so we do a computation in Z modulo 2. Always. And for example, if we take the sum of two elements and square it, then this is a squared plus b squared. Because the mixed term is 2 times something, which is 0. So this is probably a common mistake that the students do in the first semester, but here it's actually correct, right? So the squaring operation is a linear map. And so that means if we do this for powers of 2, we can look at 1 plus a. So I'm interested in this expression here, 1 plus a to a certain power. So if I do this for a power of 2, then, well, I can square it first, and I get 1 plus a squared. 1 squared is 1, of course, plus a squared to the power 2 minus 1. Keep going, I get a 1 plus a to the 2r. Okay. So that's one thing I get. And now I want to assume that this manifold is parallelizable. So assume RPN is parallelizable. And write the dimension n plus 1 plus dimension in the form power of 2 times something what. So we do that. And from this I want to conclude that m must be 1. Okay? And then I have proved the theorem. So I'm proving the theorem. And well, let's see. If we look at the Stiefel-Whitney class of the tangent bundle, since it's parallelizable, it just means that the tangent bundle is trivial. So the Stiefel-Whitney class must be 1. On the other hand, the Stiefel-Whitney class is 1 plus a to the dimension plus 1. In other words, it's 1 plus a to this number, 2 to the r times m. And this term, the 2 to the r part, I can rewrite in this form. So that is 1 plus a to 2 to the r, and the whole thing to the mth power. And now let me expand that. So if I expand that, I start with a 1, and then the next lowest term is m times this one, right? Where you have 1, 1, 1, 1, 1 times this, 1, 1, 1, 1, and this, since it's m terms, this gives you m contributions. So you have m times this term, and then higher powers of a. Plus higher powers of a. So that's what we get. And m is odd, remember? So if m modulo z, it's just 1. So that is 1 plus a, 2 to the r, plus higher powers. On the other hand, it should be 1. And so, what is this exponent here? Well, this exponent, so if m is equal to 1, then it's just n plus 1. And a to the n plus 1 is 0 in the homology of RPN. Then it's okay. If m is larger than 1, 3, 5 or so, then a to the 2, this power of 2 will be smaller than n. And then this is a contradiction to this formula. Right? So this guy here, this exponent, is smaller than or equal, let's say, to n, unless n is equal to 1, in which case it is n plus 1. And then, therefore, if m is not equal to 1, we get a contradiction. Contradiction unless n is equal to 1, which is what we want to prove. No, they cannot. Because the higher powers are independent up to the nth power, and then everything gets killed. So this cannot produce anything lower. Yeah. The higher powers are irrelevant here. Okay, so that proves this theorem. And in fact, that's a remark. So let's look what are the relevant cases here. So RP1, which is just this one. RP3, that's just this one. RP3 is SO3. And then, so this is 2 minus 1, this is 4 minus 1. Then we have 8 minus 1, RP7. These three projective spaces are indeed parallelizable. However, the next one would be RP16 minus 1 is 15, or RP32 minus 1 is 31, and the higher ones, they are not. So in this sense, the theorem is not optimal. It does not catch these cases here. If you want to rule these out, you need more sophisticated methods, operations and stuff. So, but anyway, we are on the right track, right? So that's just a remark. And now we can use this theorem here as a good tool to finally prove something that I had promised you in the very first lecture of this lecture course, namely a statement about division algebras. You may have forgotten about this by now, but I advertised the course by saying you can improve such things, and then I should also do it. So, so let's do it. So that's the theorem of Stiefel, name occurring in Stiefel-Whitney classes, not a coincidence. And so it says, suppose there is a linear map, let me call it sigma, from Rn plus Rn to Rn, without zero divisors. Then n must be a power of 2. fact, the examples that we have in mind are, well, R itself, where you just take the usual multiplication, then complex numbers, which is R2, where you take complex multiplication, then quaternions on R4, where you take the quaternion multiplication, and the Cayley numbers, or octonions on R8. So there's no assumption that this product, if you will, has to be commutative associative or anything, right? There's no such thing. The only thing that matters is that it has no zero divisors. And in fact, so this is in accordance with the theorem. The fact that there are no further ones in higher dimensions refers directly to this statement here, which I cannot prove. So these are in fact all of them. So this, right? So this corresponds to that case. This corresponds to that case, and this corresponds to that case. Let's see how this corresponds. I mean, what do these division algebras have to do with parallelizability of real projective space? So let's see that. So let me prove the theorem. All right. Okay, so let's start with the standard basis of Rn. And now let's, from this, consider following maps. So phi j, a linear map from Rn to Rn, which is just given by using this product, where one of the factors is one of these basis vectors. So phi j of x should be sigma of x and Rj. This is a linear map in x, of course. And it has non-trivial kernel because of this zero divising thing, right? So if phi of x is equal to 0, then we have a 0 here. The whole thing is 0. If that is not 0, then that would be 0, because otherwise we have a 0 divisor. So that phi j is a linear map with trivial kernel, so it's an isomorphism. Okay, phi j is an isomorphism. For dimensional reasons, it's also surveyed. Okay, good. And from this, we produce some new isomorphisms, namely Vj, also mapping from Rn to Rn, simply defined by Vj being take the inverse of phi 1 and compose with phi j. New isomorphism. Right? Now the first claim is that y1 of x, or v1 of x up to vn of x is always linearly independent, unless x is 0, of course. It's linearly independent for any x non-zero. So what is that? And okay, so proof of the claim. So let's say we take a linear combination of such these vectors for some non-trivial x and equate that to 0, and then we have to conclude from this that the coefficients must be 0. Okay, now this gives me alpha 1, phi 1 of phi 1 to minus 1 of x, well that's actually x, right? Plus and so on, alpha n, phi n of phi 1 to minus 1 of x. So that is alpha 1. And now, let's see. The definition of this phi is multiplication with the corresponding vector. So what we have here is sigma phi 1 of x is 1 plus alpha n sigma, and here we have also phi 1 minus 1 of x dn. And by linearity of the second argument, I can write this as sigma of phi 1 to minus 1 of x, alpha 1, e1, and so on, alpha n en. And that's 0. And we don't have 0 divisors. And this guy is not 0 because this x is not 0, and so that's an isomorphism. So this one is not 0. Therefore, this guy must be 0. But of course, the standard basis is linearly independent, so this implies that alpha 1 all coefficients must be 0. So that proves the claim. Right? So for each x non-zero, these are linearly independent vectors. Next. Now, still no connection to RTN, right? And so what we do next is consider y2 up to yn maps from the unit sphere Sn minus 1 to Rn, which are given as follows: yj of x is equal to, and what I really do is I take vj of x and project it to the orthogonal complement of x. X is a unit vector. So I subtract the part which is a multiple of x. So that's just the orthonormal projection onto the orthogonal complement of x. That's what I'm doing here. And it wouldn't be very meaningful to do this for v1, because v1 is just the identity. And if I do this with the identity, then I get just 0. Right? Y1 would be 0. That's not interesting. In any case, what we then have, then all these j of x's are perpendicular to x by definition, because I made them perpendicular here with this projection. And that means they are vector fields on the unit sphere. So yj is a vector field on Sn minus 1. So we have n minus 1 vector fields on Sn minus 1. Now the next claim is that these vector fields are pointwise linearly independent. So they give us, in fact, a parallelization of this unit sphere. So that's the next claim. y2 of x all the way up to yn of x linearly independent for all x in the unit sphere. Alright, what is that? Let's prove that claim. So let's put the linear combination equal to 0, eta 2, y2, plus and so forth, eta n, yn of x. Let's put this equal to 0. And we have to conclude from this that the betas must be 0. Right? And so I can just use this definition here. Then what I get is beta 2 times v2 of x minus beta 2 times the scalar factor times x. Right? For the first term, and similarly for the others, then I get beta 2 beta n vn of x minus beta n, this term is vn of x, x times x. So that's what I get. And what I have, well, we have here what? This is the same, x is the same as v1 of x. So I have a linear combination of v1, v2, and vn put to 0, but we know already from the previous claim that the v's are linearly independent. Therefore, all the coefficients occurring here must be 0. In particular, these v2 to vn must be 0. Which is what we wanted. So these y's give us actually a trivialization of the sphere, a parallelization of the sphere, trivialization of the tangent bundle of the sphere. But we want to do something actually in RPN because we have this previous theorem about parallelizability of RPN. This would not work on the sphere because the sphere doesn't have enough cohomology. So if the cohomology of the sphere is almost always 0, so characteristic classes working directly on the sphere would not give us any information. Yeah, I really have to work on RPN because this has a lot of cohomology in each dimension. And in order to do that, we observe that yj of minus x. So if I insert minus x, then I get what? Then I get vj of minus x minus. And then here again, I have vj of minus x times minus x times minus x, right? So this is by linearity of the v minus vj of x. And then let's see, how many signs do we have now? 1, 2, 3, 4. So plus vj of x, x, x. In other words, we get minus yj of x. By this formula. And what does this mean? Here we are on the sphere. Here we have x, and somewhere down here we have minus x. And now we have a vector field that has the property that the value of x is the negative of the value of minus x. And this means that the vector field descends to RPN. Because if this is represented by that curve, then the corresponding antipodal curve will be this one. And so the corresponding image in RPN is a curve in RPN which represents the corresponding vector downstairs. Right? Or otherwise, if you start with a vector field on RPN and you lift it up to the sphere, then you get exactly a vector field with this property. Okay, so therefore, vector fields, they descend to vector fields y2 bar or yn bar on RPN. And of course they are still at each point linearly independent, therefore RPN is parallelizable. And now by the previous theorem, we know that n, no, this is RPN minus 1. So we're working on Sn minus 1. RPN minus 1 is parallelizable. And then from the previous theorem, we know that the dimension of this projective space plus 1 must be a power of 2. That's just n. And that proves it. And you see, once you know this fact, I'll erase it, that the higher, that for the higher powers of 2, the thing is still not parallelizable. This proof would also give you that you cannot have a division algebra. It's the optimal theorem just requires this additional reasoning to rule out the RP15, RP31, and so forth as parallelizable spaces. All right, so now I kept my promise to prove this part, and then I want to use the final 20 minutes to complete the argument why three-dimensional manifolds are always oriented three-dimensional manifolds, compact ones at least, are always parallelizable. Remember what I did is I proved that on the three-dimensional manifold, a spin 3 bundle is always trivial. That's what I prove with this obstruction theory argument when I constructed frames inductively over the skeletons of a triangulation. Remember that? And but what we need to know is that for the tangent bundle, at least for the tangent bundle, that if it is orientable, then it is also can be lifted to a spin 3 bundle. In other words, that an orientable three-manifold is spin. That's what we need to know. And I want to use the last minutes of the lecture to indicate how one can prove that. Okay. And this also uses Stiefel-Whitney classes. That's why I'm doing it now. And as a tool for this, use the so-called Steenrod squares, which is a particular operation on cohomology with Z2 coefficients. Namely, there are linear maps denoted square upper I. So they map from the cohomology of a space M with Z2 coefficients to the cohomology shifted by degree I. With the following properties. So if I take I to be 0, then there is no shift, and then the thing is just the identity. This doesn't do anything. Now, if I apply square upper I to a cohomology class omega in degree I, so for omega in hi, then the shift just doubles the degree of the thing, and then indeed it is the same as the square of omega with respect to the cut product. So that's why they are called Steenrod squares. That's the reason. And here you see already that such a thing can certainly work only for Z2 coefficients, because the squaring operation must be a linear map. And if you apply square I omega, or let's say square upper j omega to omega in hi with j larger than I, that is 0. So that is what we need. So there are further properties what we want. And these operations are called Steenrod squares. All right. In particular, if I apply the 0 Steenrod square to 1, then since the 0 is 1 is the identity, then I get 1. And if I apply any other Steenrod square to 1, for I larger than 0, then the 1 has degree 0, so then the third one applies and I get 0. So this element 1 in H0 is mapped to itself under square 0 and is annihilated by the higher Steenrod squares. Okay. Now there is a theorem by Wu which allows one to compute the Stiefel-Whitney class of the tangent bundle for compact manifold in many cases. So let me state that theorem. So let M be a compact n-dimensional manifold. So dimensional manifold, I should say. And then there exists a class which is now called the Wu class. V equals 1 plus V1 plus V2 and so on. That's an H2, and so on. With the following property, such that Vk vanishes whenever k is larger than n minus k. N is the dimension of the manifold. And more importantly, the Stiefel-Whitney class, the case Stiefel-Whitney class of the tension bundle, is given in terms of this Wu class and the Steenrod squares. Namely, to take the Steenrod square upper I applied to Vj, and I'm supposed to get a class of degree k. So Vj has degree j. This erases the degree by I. So the degree of that thing is I plus j. So we have to sum over all I plus j equals k. So that's the Wu formula in order to compute the Stiefel-Whitney class of the tension bundle. And now, why is this helpful in particular in the case of three manifolds? Well, in this case, let's see. Now, n equals 3. All right, so let's see. This condition here is already satisfied for k equals 2. 2 is larger than 3 minus 2. And of course also for all larger k. So the only contribution actually in the Wu class, in the three-dimensional case, is the V1. So in this case we have the Wu class is 1 plus V1. Now, let's see what this tells us for the Stiefel-Whitney classes. Let's compute W1. W1 of the tension bundle is equal to square 0 of V1 plus square 1 of V0, which is 1. Right? So there are only these two terms here. Now, square 0 is the identity, so I get V1. And square 1 of 1 is 0, as I mentioned earlier, because this has degree 0. So I have V1. So in other words, the Wu class is given as 1 plus the first Stiefel-Whitney class of the tension bundle. Okay. And now let's compute the second Stiefel-Whitney class of the tension bundle. So then we have square 0 of V2 plus square 1 V1 plus square 2 of V0, which is 1. Again, this higher square of 1 is 0. And V2 is also 0, it's not there, right? So this is because of this condition here. So that this guy here is 0. And so what we get is only the middle term, which is square 1 applied to V1, but V1 is the same thing as W1. So we can express the second Stiefel-Whitney class in the three-dimensional case in terms of the first Stiefel-Whitney class, applying this square upper 1 operator to it. Now, so now there are some facts about Stiefel-Whitney classes which we want to know, namely, if F is a line bundle, so real line bundle, oh, it's not real now, a line bundle, so rank 1, then in fact F is trivial if and only if its first Stiefel-Whitney class vanishes. And we need to prove that. Certainly one direction is clear, namely if it's trivial, then the Stiefel-Whitney class vanishes. We know that. The question is, why does the opposite direction also hold? And one way to do it is to think of these bundles in terms of transition functions. If you do local trivializations, you have transition functions. In the case of a real line bundle, the transition function just takes its values GL1. You can provide it with a remainder metric, then it takes its values in O1. But O1 is the same thing as Z modulo 2 as a group. There's two elements, the matrix +1 -1. Except that, you multiply these matrices instead of adding the elements in Z2. So in other words, this bundle is described by a system of transition functions with values in Z2. And the cohomology H1 in which W1 lives, if you do this in terms of so-called check cohomology, is also something which is described by functions satisfying the co-cycle condition with values in Z2. And from that point of view, the two things are just the same. The Stiefel-Whitney class for W1 and the bundle itself are described by the same systems of transition functions. So that's behind this equivalence. Okay, now in higher rank, if F is any real vector bundle, then I claim that F is orientable if and only if W1 of F vanishes. And if you know the first statement, this may not come as such a big surprise anymore, because orientability of the bundle is equivalent to saying that the maximal exterior power of the bundle is trivial. And then the only thing you need to check is that the Stiefel-Whitney class of F and that of its maximal exterior power coincide. So that's what gives rise to this equivalence. And finally, the vanishing of the first class and of the second Stiefel-Whitney class is equivalent to F having a spin structure. I'm not saying what this means. Basically, it means you can take the frame bundle of the bundle, which is an SON bundle, and then there is a spin end bundle, which projects down to the SON bundle so that everything is compatible, and this vector bundle is an associated vector bundle to the spin bundle, not just to the SON bundle. And so that also has to be proved now, of course. If one knows these interpretations, then this computation with the Steenrod squares explains everything. Why? We were talking about three-dimensional manifolds which are orientable. So the first Stiefel-Whitney class of the tension bundle vanishes. But now we saw that in the three-dimensional case, at least on compact manifold for the tension bundle, the second Stiefel-Whitney class is the Steenrod square of the first Stiefel-Whitney class. That's a linear map. So if the first Stiefel-Whitney class vanishes, then the second Stiefel-Whitney class vanishes automatically too. And therefore, the thing does have a spin structure. So that's the usual argument given for this thing. And then if you combine everything, you know that each orientable three-manifold compact, at least, because the Bohm theorem requires compactness. Compact three-dimensional manifold orientable is polarized. So that sort of wraps things up. Yeah, so now I'm done. And are there any questions about this? Yeah, actually, yes. You don't need the splitting principle for this part. And yeah, so I mean, this depends, of course, on how exactly you define the Stiefel-Whitney classes. And you can define them by using a pullback procedure. So you prove that any real bundle on a manifold can be pulled back from some universal bundle. The base manifold of this bundle is not on a finite dimensional manifold. It's an infinite dimensional manifold, but never mind. So you can pull it back, and then each element in the cohomology of this universal base space can be pulled back and gives by naturality exactly such characteristic classes. So you have to compute the cohomology of this universal space. It's an infinite dimensional Grassmannian, in fact. And then you see that you have one generator corresponding to these degrees, etc. So the Stiefel-Whitney classes are exactly what you get. So basically, you have two choices. You can pull back a generator to 0, or can pull it back to something non-zero. And this condition that I made on the tautological bundle of RPM1 just makes sure that you pull back the non-trivial class and not the trivial class. And that's how things specify everything. It is, yeah, sure. It is the non-trivial line bundle on S1, which is the Möbius-Band. That's true. Yeah, that's correct. So there are only two line bundles on S1 or RP1, namely the trivial one and the Möbius. And since the Stiefel-Whitney class is non-trivial, it must be the Möbius. But you see this directly from the condition to also. Because if you go around RP1 once and then you associate the corresponding lines, then the line is a subspace, is a line in R2, and this line will make one pi turn. So you identify a band with -1 identity on the boundary. So from the definition of the tautological line, but you also see that it's a Möbius band. Yeah. Any further questions? Seems not to be the case. Then I thank you for your attention, your patience to stay with me until the end of the semester. And yeah, then I wish you a nice holiday.